Okay, let's continue where we were in chapter 3. All right, let's talk a little bit about formulas. We talked about this in an earlier chapter. Talked about formulas, simplest formulas, molecular formulas, also known as the true formula, and structural formulas. And we said we'd come back to it later. I said that a lot the last couple of chapters. Well, I keep my promises. It just sometimes takes me a while. So let's circle back. That seems to be the phrase these days, to formulas and talk about those. So let's talk about mass percent from formula. So what is the percent composition of, name that compound for me. That is potassium chromate. There's your chromate polyatomic ion you're supposed to know. Potassium, always +1, so no Roman numeral. So you don't say di because it's an ionic compound because you've got a metal. So this is potassium chromate. All right. So what's the percent composition? Okay, well you might say, oh, that's pretty simple. Let's see, I've got 2 atoms of potassium, a chromium, 4 oxygens. So let's see, if I want to do the chromium, let's say for example, well, one of those atoms is chromium and 7 total atoms, so 1/7 of it is chromium. So I run through the calculator, get my percentage. Is it that easy? Well, no, it's not quite that easy, okay? Because a chromium doesn't weigh the same as an oxygen, and an oxygen doesn't weigh the same as a potassium. So you can't just count up the atoms and say that that's the percent composition, okay? So how do you do this? Well, the first thing you have to be able to do is you have to be able to find the formula mass. Again, if you can't find formula mass, you're dead in the water on this problem too. See, you gotta know how to do that. So how do I find the formula mass? Well, I've got 2 potassiums. So we look in the periodic table under potassium, that's 39.10. So I'm going to multiply that by 2. We find a chromium, that's 52. And then we've got 4 oxygens there, and each of those, of course, are 16.00. So 4 times 16, that's 64, and 52, and about 78.2. Add that together, 194.20. And that's the formula mass. All right, so if you were asked what is the percent potassium in this compound, how would you do that? Well, I know the whole thing weighs 194.20. So how much of that is potassium? Well, 78.20, or 2 times 39.1, basically 2 potassiums, right? So I take whatever the mass of the potassium is, I put that over the whole thing. I don't put it over what's left. It's what you're interested in over what the entire thing weighs, multiply by 100, because that's how I get to a percent, and I get 40.3% potassium. Make sense? All right, what if you were asked, what's the percent chromium in this compound? Well, how much chromium do I have there? Well, I got 1 chromium at 52. The whole thing weighs 194.20 times 100, so it's 26.8% by mass chromium. And of course, oxygen, 4 times 16, that's my oxygen, over 194.20 times 100. And so therefore, 33.0% by mass oxygen. All right, and that's how you do it. All right, now if I add those up, what should that add up to be? Well, that should be 100%, because that's all you have in there is potassium, chromium, oxygen. Does it add up to 100%? Why doesn't it add up to 100%? Well, round off error. It might be 100.1, or it might be 99.9 or 99.8, and that's just round off error. So theoretically, yes, it should be 100%. Okay, practically, since you're rounding, it may not be. But it's going to be close. It's going to be 99.9 or 100.1 or 100.01 or something like that. It's not going to be 150. It's not going to be 62. If you add them up and it doesn't come anywhere near 100, you have done something wrong somewhere. You need to go back and check. But that's how you do it. All right. Now, why would I care? Well, okay. Well, here's an example. Let's say, for example, you want to have a nice, healthy lawn, because I know 18-year-olds are really interested in nice, healthy lawns. outside their homes. So what are you going to have to do? We're going to have to fertilize, right? Okay, so what's the main element you're trying to put into the soil when you fertilize? Well, that would be nitrogen. Okay, can you just take a handful of nitrogen from the air and shove it in the dirt? Does it work that way? Well, no. You have to find some sort of a compound that is soluble so you can get it in the ground. Okay, and so you take something like ammonium nitrate, for example, and that actually goes into the ground, and then that's your source of nitrogen. Well, let's say you're making fertilizer, and let's say you have two different compounds, one that is 60% by mass nitrogen and one that is 40% by mass nitrogen. Assuming that both compounds cost the same, assuming they cost equal amounts to make, assuming there's no waste disposal costs in the manufacture, and by the way, these things are never all the same, but assume they are, which one do you think would be better to use as a fertilizer? Well, the one that has the higher percent nitrogen, see, because you can either make smaller bags, which lowers your transportation costs, or I guess you could always just pack more nitrogen per bag, see, and beat your competition that way. All right. So yeah, percent composition does have some use out there. Okay? But that's how you calculate it. Okay. Okay. Well, this next problem is probably the longest problem in chapter 3. Very long. Okay, kind of complicated. But here's the good news. They all work exactly the same way. All right, so if you follow the steps, you can do any problem I throw at you. If you can do 2 or 3 of these without making a mistake, you can do 3,000 of them because they all work exactly the same way. It's just you got to go through the procedure, and that's kind of a pain. So what I'm going to do here is I'm going to go ahead and give you a little checklist here that you can look at. It makes a lot more sense when you do the problem, but at least this way you've got it all written in one spot and you can refer back to it when you're doing problems. And of course, on the test you won't need it anymore because you've done so many of these that it's simple. All right. So how do you do a simplest formula from a percent composition? Well, the first step is the easiest step in the whole thing, but if you don't do the first step, you can't go any further. All right, and so your first step is you assume a 100-gram sample. All right, now does it have to be 100 grams? No, you could assume a 1-gram sample. You could assume a 37-gram sample if you wanted to, but assuming a 100-gram sample makes your life a lot easier. So we'll explain. All right, then what you're going to do is you're going to convert all those grams to moles. Because when you write a formula, I'll let you in on a little preview here for later. When you see a formula like this, this says 2 atoms of potassium and 1 atom of chromium and 4 atoms of oxygen produce 1, technically, formula unit of K2CrO4. But it also says 2 moles of potassium and 1 mole of chromium and 4 moles of oxygen atoms produce 1 mole of potassium chromate. Subscripts in formulas are not only atom-to-atom ratios, they're mole-to-mole ratios. What they are not is gram-to-gram ratios. This does not say 2 grams of potassium and 1 gram of chromium and 4 grams of oxygen produce 1 gram of K2CrO4. All right? Their atom-to-atom ratios are mole-to-mole ratios. So that's why we have to convert our grams to moles here. All right? Notice if you can't go from grams to moles, you are dead in the water on this problem. Everything in this chapter builds, so go back and make sure you know how to do everything before you get to here. All right. Once you do that, you're going to set up a chart. Okay. I do that just to keep from getting confused. Not super necessary, but it certainly makes things a little easier. All right. And then what you're going to do is you're going to divide all those numbers by the smallest number in the chart. All right. When you do that, one of 2 things will happen. Either everything will come out as magically small whole numbers, in which case you're done. Write the formula. If you're not so lucky, then what you're going to do is you're going to multiply everything by 2, and then by 3, and then by 4 until you get all small whole numbers. And then you write your formula. All right. So let's take a look at that in action. So what is the simplest formula of a compound containing 26.6% by mass potassium, 35.4% by mass chromium, and 38.0% by mass oxygen? Okay, so what's our first step? Well, we're going to assume a 100-gram sample. Okay, so if I have a 100-gram sample here, how many grams of potassium do I have? Well, 26.6% of 100 is what? 26.6 grams of potassium. How many grams of chromium? 35.4 grams of chromium. How many grams of oxygen? Well, 38.0 grams of oxygen. See? So if you assume a 100-gram sample, your life is much easier. If you assume a 37-gram sample, I mean, you could sit there and figure out 26.6% of 37 if you wanted to. It'll still work, but, you know, why? Why make your life any harder than it already is, right? So just assume a 100-gram sample. Okay? All right. Step 2, what do we do? Well, now we're going to convert all these grams into moles. All right. So I've got 26.6 grams of potassium, 35.4 grams of chromium, and 38.0 grams of oxygen. All right. I'm trying to get from grams of potassium to moles of potassium. Do I know any kind of a direct relationship between grams of potassium and moles of potassium? Give me 2 equivalent quantities. For every what? For every 1 mole of potassium, that's what? 39.10 grams of potassium. Again, where did I get the 39.1? Atomic mass in the periodic table, slap of grams on the end of it. 1 mole of any element is equal to that many grams, whatever the atomic mass is. All right, 1 mole of chromium is what? 52 grams. And 1 mole of oxygen is 16.00. Again, atomic masses, all that is. All right, what goes on top, what goes on bottom? Well, you want to put the grams on the bottom because you want to cancel out the grams and you want to be left with the moles. All right, so that's how we set those up. So now we do the math. So 26.6 divided by 39.10. 3 significant figures here, 4 here. So my answer needs to have 3. So I'm multiplying here. So that would be 0.680 moles of potassium. All right. 35.4 times 1 divided by 52.00. 3 significant figures here, 4 here. 3 in my answer, 0.681 moles of chromium. 38.0 divided by 16.00, 3 here, 4 here, 2.38 moles of oxygen. All right? So, third step, we're going to take those numbers and we're going to put them in a little chart here. Okay, so here's potassium to chromium to oxygen. There's my numbers. All right, now what am I going to do? Well, I'm going to divide by the smallest number in the chart, and the smallest number in the chart happens to be 0.680. All right, now why do I do that? Well, because you can't have 0.68 of an atom. You can't have 2.38 oxygen atoms. You know, either you've got 2 or you've got 3. You can't have 0.38 of an atom. So I need a ratio there that's all whole numbers. All right, if I divide everything by the smallest number, the absolute worst case scenario is one of them comes out a nice small whole number, and that's namely the smallest one. 0.680 divided by 0.680 is what? What's 1? See? So if you're lucky, they're all small whole numbers. But if you're not lucky, well, the worst case scenario is at least one of them is a small whole number. So that's what we're going to do. So 0.680 divided by 0.680 is 1. 0.681 divided by 0.680 is really, really, really close to 1. By the way, hypothetically, should that have been exactly 1? Yes. Why didn't it turn out to be 1 exactly? Experimental error. Again, experimental error. All right. 2.38 divided by 0.680 is 3.5. Is that close enough to a whole number I could just go ahead and round that up or round it down? No, that's probably actually in the data. So you need to leave that as 3.5. All right, so I guess your next question would probably be, how do I know when to round up or when to round down or to leave it alone? Well, the answer is it depends on how well you did the experiment. See, if you went in the lab and kind of slopped around, then yeah, you're going to have a lot of error in your data, and you're not going to know where to round. You know, is this too far away from a whole number? Is this too close to a whole number? So on and so forth. If you went into the laboratory and you did the experiment very carefully and very accurately and very precisely, then you'll be very close to a whole number. You'll be able to tell right away whether you need to round up or round down. You know, what you do in lab the first 2.5 to 3 hours makes your life either easy or hard the last hour. You know, when you get good data, decisions are nice and simple. When you have bad data, then that's when you have to sit there and agonize over it and take guesses. Well, is this right? Is this right? And that's when you start missing stuff, and that's when your grade goes down. So, you know, spend the time and do the experiment properly and correctly. So that way you don't have to make any decisions. You know, your life's stressful enough. Why do you need to make more decisions, right? Okay. Now, in the book, you know, because this is the book, not in the lab, how do I know when to round up or round down? I guess would be your real question there. General rule of thumb. If you're within about 0.2, usually I go ahead and round up or round down for problems in the book. So if I had like 1.85 or 1.9, I'd probably round that to 2. If I had 1.75, I'd probably leave that as 1.75. So 0.2 seems to be about the break point for most problems in a chemistry textbook. All right, but in lab, it really kind of depends on how well you do the experiment, I guess. In this case, the 3.5 is actually probably in the data, so we're leaving that there. All right, so I've got a 1-to-1 to 3.5. Do I have all small whole numbers? No. Okay, so what we're going to do is we're going to multiply those by 2 and see if we get all small whole numbers. If that doesn't work, we're going to go right back up here. We're going to multiply everything by 3. If it doesn't work, we'll multiply everything by 4, and so on and so on and so forth. So in this case, multiplying by 2, 1 times 2 is 2. 1 times 2 is 2. 3.5 times 2 is 7. All right, are those small whole numbers? Yes, they are. All right, so you are ready to write the formula. So my formula is K2 Cr2O7. And that is the simplest formula. Now in this case, the simplest formula actually happens to be the actual true formula. Is that always the case? No, that's not always the case, but in this case it is. So can you name that compound for me? Well, that is potassium dichromate. It's potassium dichromate, Cr2O7. Is it long? Yeah, it's kind of long. Do they all work the same way? Yes. If you can get through 3 or 4 of these, you can do any of them. All right, let's see another one. Molecular formula from simplest formula. What's the molecular formula? Well, the molecular formula, if you'll remember, is the true formula. It's the actual number of atoms in a molecule of the compound. It turns out that you can get the true formula, or the molecular formula, from the simplest formula, but you got to know one more piece of information. And that piece of information is the molar mass. So if you can get the molar mass of the compound and you can get the simplest formula, you can get the molecular formula. All right, now how do I get the molar mass if I don't have a formula? There are ways. It's actually possible. You know, we'll probably talk about one this semester, and probably next semester we'll show you another way to do it. You can actually get the molar mass without even knowing the formula, without even knowing what's in the compound. All right, in lab. And yeah, we'll show you that in lab later on. All right, so here is acetic acid. Okay, and acetic acid contains 40.0% by mass carbon, 6.70% by mass hydrogen, and 53.3% by mass oxygen. All right, if 2.5 moles of acetic acid weigh 150.15 grams, what is the molecular formula, or the true formula, same thing, for acetic acid? Okay, so the first thing I have to do to get this problem done is I got to get the simplest formula first. And then I'm going to use this other piece of information over here to try to figure out the molecular formula. All right, so what's the first thing we do? Well, we assume a 100-gram sample. So that's kind of what we're going to do. So How many grams of carbon do I have? Well, I got 40.0 grams of carbon. I got 6.70 grams of hydrogen, and I got 53.3 grams of oxygen. All right. Then what do? Well, we convert those to moles. So here's my 40 grams, my 6.7, and my 53.3 grams of oxygen. Okay. 1 mole of carbon weighs 12.01 grams. Atomic mass periodic table. Grams on the bottom here, so they cancel. We're left with moles. 1 mole of hydrogen, 1.008 grams. And 1 mole of oxygen, 16. Okay, grams cancel, grams cancel. So what am I left with? Well, 40.0 divided by 12.01, 3 significant figures here, 4 here, 3 here, 3.33 moles of carbon. 6.70 divided by 1.008, 3 significant figures here, 4 here, so my answer needs to have 6.65 moles of hydrogen. And 53.3 grams of oxygen divided by 16.00, 3 here, 4 here, 3 significant figures here, 3.33 moles of oxygen. All right. What do we do in step 3? Well, we set up the chart. Okay, so we're going to set up our little chart here. So I've got 3.33 moles of carbon, 6.65 moles of hydrogen, 3.33 moles of oxygen. All right, so we're going to divide by the smallest number. So the smallest number in the chart is what? 3.33. So 3.33 divided by 3.33 is 1. 6.65 divided by 3.33 is pretty darn close to 2. And 3.33 divided by 3.33 is 1. So dividing these by the smallest number gives me a 1 to 2 to 1. Do I have to start multiplying by 2 and 3 and 4? No, because I've already got small whole numbers. So therefore, the simplest formula for acetic acid is C1H2O. And there's your simplest formula. Can you do it? Okay, now how do I get the true formula for acetic acid? Is CH2O the actual true formula for acetic acid? Maybe, could be. Sometimes the simplest formula is the true formula or the molecular formula, but sometimes it's not. So how am I going to figure that out? Well, I need to figure out the molar mass somehow. So how am I going to do that? Well, I know that 2.5 moles of acetic acid weigh 150.15 grams. All right, so molar mass is what? Grams per mole. So I just simply take my grams here and divide it by the number of moles. Grams per mole, see? There we go. So 150.15 divided by 2.550. 5 significant figures here, 4 here. So my answer is to 4. 60.06 grams per mole. All right? Okay. So, is this the true formula for acetic acid? Well, it is if you add these numbers up over here and it adds up to 60. If this adds up to 60, then yeah, the simplest formula is the true formula. So I find the molar mass of my simplest formula here. So I've essentially got roughly what? 12, 13, 14, 14, and 16. So it's roughly 30, 30.03 if you want to go ahead and add it up correctly. But something like that. It's not 60.06. All right, so what that tells me is the true formula for acetic acid is not the same as the simplest formula. Otherwise, it would add up to be the same, molar mass-wise. So how do I find the true formula? Well, here's what you're going to do. You're going to take the molar mass of your molecular formula, and you're going to divide that by the molar mass of your simplest formula. And when you do, what you'll get is you'll get a whole number. You know, you'll get a 1, a 2, a 3, a 4, a 5, or something like that. And then what you do is you simply multiply your simplest formula by whatever number you get there. So 60.06 divided by 30.03 ends up being 2. So we're going to multiply our simplest formula by 2. So the molecular formula, or the true formula of acetic acid, is C2H4O2. And that's how many carbons, how many hydrogens, how many oxygens an acetic acid molecule has. Do you see why the simplest formula for acetic acid is CH2O? 2 to 4 to 2 reduces down to 1 to 2 to 1. But this is the molecular or the true formula. Make sense? So if you have this and you have the molar mass, you can get this. How are those atoms put together? What's the structural formula for acetic acid? Well, that's a little harder to get. To get the structural formula for acetic acid, spectroscopy is probably the easiest way to go. This is going to require a lot more money. It's going to require a lot more expertise, more than you probably have at this point. When you get to organic chemistry, we'll talk about some ways to actually get the structural formula for molecules. But that requires some expensive machinery to be able to do. All right. Probably the easiest way to do this, you're not responsible for this, by the way. Easiest way to do this would probably be, I'd probably do infrared spectroscopy here. In infrared spectroscopy, basically you shine infrared radiation, which is a fancy word for heat, basically. And the bonds in the molecules vibrate and bend. So instead of being like little rigid sticks, like a little stick and ball model that you've seen, they're more like springs, and so they kind of oscillate. The little atoms kind of oscillate, and they bend, and they twist, and this and that. And depending on their masses and the length of the bonds, they will absorb certain frequencies or wavelengths of that infrared radiation. And so you can shine radiation, wavelengths of infrared radiation on the molecule, and it will absorb certain wavelengths, and that gives you structural information. So, for example, if we did acetic acid, you probably see something that looks really similar to this, which looks like a mess. But basically, there's a couple of things here that are really interesting. You see that long peak that goes down? The peaks go down in infrared radiation, infrared spectra, by the way, around 1725, 1720, 1700, something like that. That's a carbonyl stretch. That's a C double bond O that's kind of stretching like that. So that tells me there's a carbonyl group in there somewhere. All right, you see that big kind of wide peak somewhere around 3,000? Generally, that's shifted over toward about 3,500. But when I see that big wide thing around 3,000 and I see a carbonyl there, that just screams carboxylic acid. That big wide giant peak, which goes down, I guess is really a trough, that's an OH stretch. That's an oxygen-hydrogen stretch. So that means one of two things. Either you've got water in your sample, quit it, or you've got some sort of an alcohol. Now, if it's out around 3,500, it's usually an alcohol. If I see that carbonyl and I see that thing shifted over toward 3,000, that just screams carboxylic acid. So now it's a question of how do I put together 2 carbons, 4 oxygens, and 2 carbons, 2 oxygens, and 4 hydrogens in such a way that has a C double bond O and an OH and doesn't have 18 electrons around the oxygen or something like that, something reasonable. And so what we do is we come up with something that looks maybe like this right here. Okay, see, there's my C double bond O. Here's my, by the way, that long peak down there around 1,300 or so, that's probably this C single bond O stretch more than likely. You know, sometimes you have peaks in there you just can't assign because it's complicated. There's lots of CH stretches and second overtones, and it's a big mess. But you look at the main functional group peaks to try to figure out what's going on there. So that 1,300 peaks probably this right here if I had to guess. But there's my C double bond O, and there's my OH, and that is a carboxylic acid, by the way. And you see that C double bond O, and then the O, this is the H that comes off. This is acidic. These are not acidic. This one is. Why? We'll talk about someday. But yeah, that's acetic acid. So here's the structural formula. See, this tells you how many atoms you've got and also how they're put together. All right, now which one of these do you think is the easiest to get? Well, the one that tells me the least amount of information, the simplest formula. Which one of these do you think is the most costly and complicated and hard to get? Well, the one that tells you the most information. That would be the structural formula. And unfortunately, that's the way it works sometimes in science. The more useful a piece of information is, usually the harder it is to get it, and the more money it's going to cost you to get it as well. All right. Generally speaking, you don't want to stop here. This is usually used to get this. And then once you get this, then you can somehow figure out a way to get here. Rarely do people get simplest formulas anymore. In the old days, back in the 20th and 19th century, what people would do is they take a compound, they would degrade the compound, they would break it down to its individual elements, they would weigh it, they would get the percent composition, they would figure out the simplest formula. Then they would use another technique to get the molar mass and use that to get the molecular formula. These days we have all sorts of NMR and R and all sorts of UV vis, fancy spectroscopy, and even spectrometry if you want to do mass spec, and you can get this stuff more directly. You don't have to do this quite so much anymore. But yeah, that's how you get to here. Sometimes you can't get there in one step. You gotta make your way through. All right, but that's how you figure those out. All right, again, probably the longest problem in this chapter. If you can do this, there's nothing longer in the chapter. But again, they all work the same way. So that makes it nice and simple. Well, not simple. All right. Okay, you ready to talk about something else? Let's talk about something else. Let's talk about solutions. All right. So when you go into the laboratory, not everything you deal with is a solid, a liquid, or a gas. Sometimes you have things mixed up in water. You have things in solution. So what is a solution anyway? Well, a solution consists of two parts. You have what's called a solute, and you have what's called a solvent. All right. The solute is whatever you have less of. The solvent is whatever you have more of. So it's really kind of arbitrary in a sense. If I had a 30% alcohol and 70% water, my alcohol is my solute, and my water, of course, would be my solvent. But alcohol and water are miscible. In other words, you can have any combination of it you want. They thoroughly mix. And so if I had 80% alcohol and 20% water, well, now my water becomes my solute, and my alcohol becomes my solvent. All right. What we deal with in general chemistry are what we call aqueous solutions. And aqueous solutions means my solvent is going to be the water. All right. Why do we deal with that? Well, because there are so many of them. We have literally oceans of them. The ocean is a big, giant aqueous solution if you think about it. You're a big, giant aqueous solution. You're about 60 to 80% water and all sorts of things kind of mixed up in there in a big, giant skin-filled balloon with all sorts of chemicals that make you you. But yeah, that's, aqueous solutions are important. All right. Does everything go into water? No. There are other, what we call non-aqueous solutions. But we probably will not deal with that in here. When you get to organic chemistry, we'll deal with non-aqueous solutions. But in here, most of the stuff we deal with, water is going to be the solvent. All right. So let's say, for example, I've got a salt water solution, and I want to know how much salt's in there. Well, I guess I could put it on the scale, right? Would that be a good way to tell how much salt is in there? Well, I mean, you weigh it. You're weighing the salt, aren't you? Well, you are weighing the salt, but the problem is you're also weighing what? You're weighing the water. So how much of that is actually salt? Well, I guess the one that's bigger, the one I had more liters of, would have more salt. Is it possible to have a large volume of a solution and it actually contains less salt than a small volume of another solution? Yes, if they have different concentrations. I might have one that's very weak and I might have one that's very concentrated. So when you deal with solutions, there's two factors you have to take into account. You have to take into account the volume of the solution that you're dealing with, but you also have to worry about the concentration of the solution. So I guess if we're going to talk about solutions, I guess the next place we need to go is we need to talk about concentration. And it turns out there are many different ways that you can express concentration. Okay, we're going to talk about the big one. We're going to talk about molarity next time. That's probably the one that we're going to use more than anything else. But we'll talk about a few others, and we'll talk about where those are used, and we'll do some calculations with that because I know you guys just really, really love math. The more math, the better. So we'll put some math in there for you, and then we'll go from there. So seems like a decent place to stop. So I guess we'll see you in the next video. So bye for now.